Okay, good morning, everyone. We are Project Fortunas. This is the project we've been working on all year. And just to let you know, one of our teammates did test positive for COVID this morning, so he'll be Zooming in to present with us. Okay, to start, my name is Matthew. I handled the software end and the mobile app development.
Hi everyone, I'm Nazar and I work at PC Design.
Hi, I'm Charanpreet Singh and I worked on the GPS development.
Hi everyone, my name is Noah. I worked on the PCB as well with the CAN bus.
Ooh, okay. So the problem. So basically, a lot of new cars have partner apps to control their vehicles. When we see with like new Teslas, there are a lot of like mobile remote control features to lock and unlock, start, stop, control windows, all that stuff. So basically, to add these features onto a car that doesn't have these, there's no universal method of doing so because most of these features come specific with proprietary software to specific make and models. So there's no universal method currently of doing that. So our solution is a plug and play module that would plug into the OBD2 port of any car, and we'll explain more what that means later. So what this would allow us to do is to wirelessly lock and unlock any vehicle, would give us GPS tracking as well as reading diagnostic data from our control unit of our car. And here is a demo video just to demonstrate what that looks like.
The Project Fortunas module is a plug-and-play solution that allows you to control, track, and view diagnostics from your vehicle. The module is installed using the OBD2 port under your steering wheel. You can connect it via the OBD2 68K plus. Using the integrated app, we can check the car's gear. Yeah, check the cars right here. And you can check the car's license. Additionally, the module includes GPS tracking. Coordinates are collected to the fire date of the top select. The app then plots the points on a Google Map interface. Lastly, on select vehicles, the module is able to unlock and lock the vehicle. This is Project Fortunas. Thank you for joining us. The Project Fortunas module is plug-and-play. So now moving on to the block diagram. Started with the GPS and GSM controller. So the reason why we chose this part in particular is because it's economical and it fits exactly the Raspberry Pi that we're using with it. It gets the job done. And the important part is it has both the GPS and the GSM module. That means we can connect to the cellular towers, and we can send our data over to the phone using cellular data, and that is important. So, like, no matter how far the vehicle is away from you, we can still send or receive data, and that's like in Wi-Fi or Bluetooth for these. So next is the Raspberry Pi Zero W. This is the glue that holds together both the GPS module and our custom PCB, and we chose it because it's still very small. It draws very low power, so if you want to leave the module plugged into your car, it won't drain the battery. And another important part about the Raspberry Pi is that it will run Python, and that is what we use to communicate with the CAN bus car. And this is our custom PCB. On it is the CAN controller, and that is what we use to actually talk with the car's control computers. And we connect, we connect the car through the OBD2 port. This will be shown in the demo, and this is the D9 connector that is on our PCB. So next is the schematic, starting with the 42 connectors here. This is our custom module connected to the Raspberry Pi, that's all necessary things. Then is the actual CAN transceiver right here for the controller. So the transceiver part of the module is the part that actually gets the codes from the car, and this is the controller is how we can actually use stuff with it. Next is the power diode right here. That works in conjunction with the buck converter to power the Pi. So the Pi actually gives the power straight to the car. And the diode is here is so the Pi can be private, and the buck converter converts the 12 volts in the car to the 5 volts that is necessary for the Pi, and that's the UV9 board that we actually connect the car. And here is our layout. The 40 pin connector. I think my microphone just died. Can you still hear me? Yeah. Okay. So the 40 pin connector, the power converter module, the CAN controller, and transceiver with the diode parts, and this is the DB9. As you can see, the dimensions, the width is the same as Raspberry Pi, so it's neatly on it. We just have to make it a little longer to fit the DB9 connector. We went through a couple different iterations. We used for the new one, we used different power converter because you need a higher range for voltages to get from the car, and we also fixed some of the pin outs from the new model.
So one of the most important questions that we have is, how do we even talk to the car? Well, ever since the 90s, cars have been using CAN, or Controller Area Network, which is a bus-based protocol that connects all the car's systems together. And since all modern cars have CAN, as long as we have some device that's able to sniff the bus, we can essentially sniff out all the systems within the car, such as the power locks, engine, etc. And every car also thankfully has an onboard diagnostics port that is also connected to the CAN bus. And so as long as we have some way to connect to the CAN bus using the onboard diagnostics, we can sniff messages and be able to read what's happening with the car and send messages back. So in terms of our project, like we said in the video, we connect to the car using the OBD2 port and plugging it into the DB9 on our CAN controller. And from there, the CAN controller is able to read the data frames and send it over SPI to the Raspberry Pi. So the nice thing about the CAN frames that we can read using a Python library called PyCAN, we can essentially read the timestamps of these messages as well as the ID of the device and the data inside. And so from there, essentially, we can reverse engineer the CAN bus. So we end up picking up a particular behavior we want to look at, such as the lights, whether they are on or off, and look for a corresponding ID that behaves with the action that we're doing. And so once we find an ID that's behaving with what we're doing physically in the real world, we're able to store that ID as well as the message that it's displaying and coordinate what that is. We can put that in a library somewhere, put that in a file, and we can store it for later so that we can use it either for reference to read a diagnostic or control the car. And as said in the video, with the locks, those are limited to particular vehicles. So when it comes to finding these IDs, it doesn't necessarily mean that you have control of the car. In the video, we are using a Ford vehicle, and we found that really only Ford vehicles were able to do lock and unlock. And that has to do primarily with security measures that are on particular makes of vehicles. If we were able to contact the manufacturers of these vehicles, we may be able to determine to see what we can do to get around security measures to unlock the car over the CAN bus, but in this case, only Ford. So just because you have found a particular ID that corresponds to say something like the locks, it doesn't mean you'll be able to control them.
So there's so for GPS tracking, there's three main steps. We first start off with getting the locational data from the GPS and the GSM module. So the GPS gets the locational data through the use of satellites and a GPS antenna, and the GSM module gets locational data through the cellular network. And we combine those to get a more accurate location so that we are getting pinpoint accuracy. Next up, we create a cellular connection using a T-Mobile SIM card. So this goes into the GPS and GSM module. We then create the connection using a point-to-point protocol. So it connects over the serial port of the Raspberry Pi, and the Raspberry Pi then has an internet connection. So once we have this and we have the locational data from the GPS module, we are then able to upload it to Firebase, which is a Google service that provides real-time database. So this allows us to send locational data from basically anywhere, and we don't have to be within the range of the actual vehicle or the device itself. So this allows us to get data of the vehicle that is plugged into from anywhere. And so, yeah.
Okay, so for the mobile application, we decided to do most of the development using Android Studio. So it's an Android-based application. As mentioned before, we are storing all this data in the cloud with Google Firebase's real-time database. And we basically have asynchronous event listeners all over the app that listen for a data change in our database and update our app accordingly for the user. And so this allows us to retrieve diagnostic data in real time and also organize GPS data and plot it using Google Maps API, which we see here. Here's our landing page where we select a user action. And to the right of that is our diagnostics data where we can read in live time our RPM, gear shift data, whether the lights are on, and then we also have GPS coordinates, which get plotted on the very right over there in real time as they're being updated.
So in conclusion, so in this project, we were able to establish a connection to the car's CAN bus. This is through the use of, for Ford vehicles at least, this was allowing us to do the lock and unlock feature. And to any other cars manufacturers, like the Honda that we used in the video, we are able to retrieve diagnostic data, which is the light, the gear, and as well as the RPM of the vehicle. We then send this data, both the GPS and the diagnostic data, using Firebase. And so this is sent to the real-time database and ultimately being pulled from the by the app so that we can get it in from anywhere. Sorry. And lastly, locking and unlocking is feasible with only certain car manufacturers, and for right now, it's only Ford. Just because their security on the CAN bus is not as secure as other vehicles. And I'd like to say a special thanks to Professor Yoga, our two TAs, Chris and Bryson, and lastly, our three representatives from Authenticate, Chad, Evan, and Rita. Thank you.
So in terms of capabilities, you're talking about things that are sort of like one-to-one with the capabilities of the car, open the door, close the door, track a data point. You have 6 more maps. So what are some like more complex features that you could build sort of like layer on top of that feature set?
So right now, like, because the a lot like locking and unlocking is only still sort of models, that also goes for like other features where you want to send actual command to the car. So before, for example, you smart things that you can just control through it is almost anything that you can do like with your key fob or like, through the user interface, so, like lights, like climate control, like volume on the radio, all this stuff, like anything that's going to actually connect you to the CAN bus of the car, which is pretty much any computer part of the car. If we have the codes to access that, like if you get in touch with the car manufacturers, then they give us those IDs. All of those would be easily accessible through this one.
Have you guys thought about making it smaller in size?
I think that's definitely possible also because Because the part that you chose are for the people of concept and they're cheaper, but I'm sure you can get a smaller GPS one or compact, make the size customizable smaller. Like not use the DB9 but something else, you know.
Any other questions?
Were you able to validate that if you have the code from the car manufacturer, are you able to make these actually work with any car as long as you have the code from the manufacturer?
We haven't done any questioning comment, but the idea is there's actual security measures for each ID. But even though the ID you get in the vehicle, but like other cars have their own proprietary software that allows them to go past it. So I'm sure there's ways to do that.
Did you do anything connected to the various warning lights and the things that warn the drivers about various conditions on the dashboard?
No, we did not.
We did not yet.
And one of the things I would be interested in when the check engine light comes on, of course, you know, what actually hails the car. It's vague.
Yeah.
It's the codes. I guess that is something that we really look into because there's so many, you know, things for that you can buy, and we felt like there's so many mobile applications for this type of data. But it's still just another protocol that can be accessed through the canvas.
And I think that also there are also other components to it that are not related to campus bugs. When we first started this project, one of our goals was to have start and stop be one of the features for the car, but that obviously that takes a lot more than just the control unit of the car. There's a lot you have to do like mechanically with the engine and all that. So yeah, there would be a lot more that would go into that.
I would also just like to add real quickly that when it comes to working with devices on the CAN bus, a lot of cars actually include a high speed and a medium speed bus. And through the OBD2 port, most vehicles only include a high speed, which is particularly just for diagnostics, which we learned later on into the project. And so that actually does create limitations as well as to what you can and cannot access off the bat.
Thank you.
We have 2 months. Yeah, that's it. Oh, okay.
Good morning, everyone. We are from my name is Ian.
Hi everyone, I'm Hongming.
Hi, I'm Joshua.
The problem we are trying to solve is related to finding parking slots. Well, every year drivers in the United States spend an average of $70 finding spots. And during this same average, $345 always did not have gas. This situation is much more in urban areas. Just New York's, it cost New York City itself $4.2 billion in this issue. So with this project in mind, can we design a small parking system that allows the driver to drive real time off the seat? So the user don't need to spend time looking for spots. And what's even more, can we do it while employees are So most LED solutions today requires that they have a student cloud for presentation, and that can be privacy issues. So the bigger contribution that we design is HW systems that solve the problem while ensuring user privacy. There are multiple solutions. So in a multi-floor computer, we will mount multi-detector unit throughout the whole parking lot. And each detector unit will consist of a camera that will power both thoughts and and a yeah and a microcontroller that's capable of running convolutional neural network model for detecting cars. And after the car detector is computed, it will be transmitted through a wireless communication protocol called LoRa to a central to a server that will save the function status to the database. Then be ready on the now let's take a look at the gateway and the architecture unit design. So on the left is the gateway server that on this page, a channel gateway, and a Raspberry Pi for hosting the network server. This gateway server can be connected to over 100 detectors on the right. And the detector unit consists of a tiny image sensor and a microcontroller that's capable of running multi-level solution. And then there's the LoRa transceiver.
So next we will be going over the hardwares. So for the microcontroller unit, we have used Max 78,000. It is a small, low-power microcontroller unit built for neural network applications. So it features a ARM Cortex-M4 processor, which can run up to 100 megahertz. So why we choose this is that it has a convolutional neural network accelerator on board that allows us to perform neural network operations and do all the classification locally. Next, let's look at each of the peripherals. So for the image sensor, we use the OVM 7692. It's a CMOS VGA camera. It has an optical size of 1/13 inch and active array pixel of 640 by 480. It also has some auto adjustment features such as the auto exposure control, which helps to maintain the image constant brightness and exposure in like different lighting conditions. Next is the LoRa transceiver. It's the RFM95W. It features a full duplex communication. It runs on a bandwidth of ranging from 7.8 to 500 megahertz kilohertz. Sorry. It's tiny. It has dimension of 16 millimeter by 16 millimeter. It communicates with the microcontroller directly through a SPI interface, and it also has an optional antenna that can be added onto it. And here's the gateway server. It's consisted of a Raspberry Pi 4, which is to host the LoRaWAN stack network stack, and rack 2247 gateway, which is to receive data package from each of the LoRa transceiver units. The gateway has a 8-channel communication, which is powered by 3 different LoRa chips on board. The gateway is also connected to an antenna, which maximizes its range, and it communicates with the Raspberry Pi through a SPI head connector. So next is the block diagram. So this is the block diagram for our system. All the hardware that I have mentioned can be found somewhere in this block diagram. The block diagram provides an overview of how data is flowed from each of the car detection unit, as shown on the left, to the central server, which is in the right, and how it eventually gets sent to the web app, which is shown in the right side.
Okay, so I'm going to talk a little bit about car detection. And again, all the detection is performed on the nodes that are distributed around the car. And so, as we mentioned, our camera is able to take pictures of up to 640 by 480 pixel resolution. However, in practice, we found that our clusters only able to handle resolutions up to 128 by 128 RGB 888 or 240 by 160 RGB 565. And RGB 888 and 565 are just two different ways of storing pixels, but we opted to go with RGB 565 because we were getting a higher resolution. So after an image is captured on one of our nodes, we segment it for 64 by 64 pixel image blocks, as you can see on the right here. And each block represents a single target space. And once we get these 4 blocks, we feed them sequentially into a CNN model, which supports vehicle detection. And the CNN model basically outputs whether or not a vehicle is found in the image. And for our CNN model, we chose an architecture that has 6 convolutional layers followed by 1 fully connected layer that has over 54,000 parameters. And the reason we settled on this particular architecture was because we found that it offered the best balance between performance and processing time. And for our training data set, we took images from a Chicago data set as well. We augmented it with our own data by collecting images here at UCSB. And here are some examples of our training data. To the left, we have images of cars, and on the right are where there's no cars. And to make our model more robust, we perform data augmentation. So this consists of transformations like rotation, reflective skew, horizontal flipping, brightness adjustment. And the resulting training data set we use is over 27,000 images. And here at the bottom, you can see an example of data augmentation being applied to the example. And so here's some metrics about our CNN model. So as I mentioned, there's over 54,000 8-bit weight. We trained it for 55 epochs. We accuracy of 96.9 on validation data set. In practice, when we tested in the field, it was closer to 88% accuracy, and we attributed this difference in accuracy to less than ideal lighting conditions, like noise environment. And running on the Max 78,000 chip, our model has an inference time of 4.25 milliseconds. And on the right here is a graph of our so after the onboard detection, we slowly sent to the server view law and to migrate to web targets. So why do we choose LoRa? So LoRa can transmit data really long range in the urban setting. You can transmit up to 3 miles, more than enough for parking lots. And while doing well, consuming low power. The only trade-off is that it's low bandwidth. The maximum bandwidth you can transmit is 27,000 bits per second. However, this won't be an issue for our system because we're only transmitting 1 byte of data from each packet weakness. And then we will talk about the network layer based on LoRaWAN. So the LoRaWAN network used for PerfStack is something I'm very proud of. Here's a block diagram that shows how data is flowing inside this architecture. So from the LoRa and logger, we see the package will be forwarded to the grid on the Raspberry Pi. And the gateway will be coded package into JSON format. And after that, the network server authenticated data and further routed to the package server. The package server will parse the parse stacks from the JSON data and encrypt it and send to Firebase to HTTP. And the package server also holds the web interface device management. And it is also integrated with PostgreSQL. So PostgreSQL is the database that stores all the necessary information to set up the server. And the database will also store all the device code and the device events are deployed. And you also have a list of users that can access the server data. And next there, and the second database this Firebase is used to store all the slot status. And the very you use that is good to get rid of this React Native.
So next, we'll talk about the software application of our project. So here's the current version of our software stack. So as previously said, after data is getting from the PyTorch convolutional neural network, it is passed on to the LoRaWAN network server via LoRaWAN communication protocol. Then it is passed on to Firebase with HTTP request, and then it is eventually rendered onto our React front end. So here's a phone view of our app. We chose to do a web app because it is cross-platform, and the user can use it without any installation of any apps. And here's a URL and a QR code if you're interested to check it out. It is also on our poster if you want to check it out later. So here's the main part of our project. After getting the status data, it is rendered onto this simplified version of map of UCSB parking lot 10. This is a one floor. And then as you can see on the parking spot, the spot status is green when it's available, and then it is red when it's occupied. The user can also use a floor selector to select different floors they want to check out on the lot. And then it also shows the occupancy numbers and the percentage of the current floor. So next is a demo video of our project. Okay, next we want to go over the battery life. So here's some of the measurement that we took during our field test. As you can see, the power operation as well as the power consumption. So with this measurement, we estimated that our system can run for a period of 3 months without an external power source. But we are looking to improve that to over a year, simply by replacing it with a larger capacity battery, and also increasing the idle time or just optimizing the code itself.
the solution unit cost is lower because they're using a super sensor and super monitor. Instead of we having the camera and the CNS area. However, our advantage is that each of our unit can have 4 slots. Compared to the approach that only has 1 per slot, each that require 1 per slot. So we probably about that same. So in overall, our system cost will be lower. All our unit cost is a bit higher, but it is that because the camera is only lost as much as possible. It's $10 itself, so it's so the trade-off is it's not that big of a with the unit required and, and, uh, and in addition, we also have a less installation and future maintenance costs because we don't go on every slot, which is just not really have policy. And the next hardware system is the visualization. So you might on the right just mount more advanced camera and a powerful computer that you can take like dozens of hundreds at a time. But the issue with this approach is that you cannot handle one shot as well as so there's no way you can have one camera that's covering the whole floor. So our system is more versatile. And in addition, because our system uses HW privacy, its privacy is ensured. Like in a central camera system, we will need to send the camera signal. You need to send the camera signal back to the server for processing and for privacy. So future, strong and small implementation. Yeah. So highly long sense to the advice from small fingers and there you go, right? Chris, yeah, a lot of engineering for helping us on this project.
How does the camera know which spot is actually monitored?
So like I think most of that comes during like a setup. So we just space the camera and add 4 slots, and it just segments the news directly for that.
And you're translating that to the UI, so
Oh,
there's a setting somewhere that says camera X has spot.
right. So that would be our combination road network. So each one will detect whether or not there's. Oh, so you're saying, I see. So,
Map this.
right. That's also the way we did it was just to set up like we just manually mapped it.
I think in the actual implementation, the device will be assigned to a certain spot number that corresponding to the spot on the server that will be displayed on the UI. So yeah, it will have a certain ID to it to each device.
What is the main reason for false positives or false negatives with regards to the color of the car that matter? What was the deal with, when you get false positives or false negatives? What's the color of the car that made a difference with regards to
I think
identification?
the biggest problem we had was just lighting, like in the parking lot, there's a lot of different, little wide range of light conditions. And I think that probably was the main, like when we did get false positives, the false negatives, usually because the weird lighting.
Did the algorithm use the color images or did you?
Oh yeah, we saw it.
Cool, thank you. Over there with Thomas. On that side with Thomas. I mean, it works right here, but okay. If whoever's here, just stay on top of it. Like, I'll give you like a little nod.
Wait, how many touch sides are there like same side?
You can please the laser. Yeah. Let's look at the laser. I think I can use it. Here, yeah. Hi everyone, we're the Opto 3D team. My name is Matt.
Oh, I'm Sunil.
I'm Ryan.
I'm Thomas. And Remy couldn't be here today. So our project is based on an existing product from Alcon. Alcon developed a stereo camera that can be mounted on a microscope used for eye surgery. It replaces the traditional eyepiece that would be there and allows an image to be displayed on a 3D monitor and provides the surgeon with better depth of field, flexible color adjustments, and ease of use. It also allows everyone else in the operating theater to see what's going on under that microscope. The problem is that there's a powerful host computer required to act as the middleman. The computer is responsible for handling any of the video capture, video processing, and interlacing necessary before outputting the 3D video to the monitor or the TV. And our goal is to bypass the need for that computer by replacing it with a smaller and cheaper, more efficient embedded system. So here's what one of the a typical operating theater might look like. That little module right there is the 3D camera and replaces the eyepiece that the surgeon would usually use. At the foot of the bed is the 3D monitor, 3D TV, and that big box under there is the enclosure that usually houses the host computer. So 3D video works by mimicking what our eyes see. Humans get depth and distance perception because our left and right eyes see slightly different images, and from that we perceive depth and distance. So a 3D monitor replicates that by, instead of showing just one image, like in 2D video, it's showing you two images, a different one for the left and another one for the right eye. To show these two different images on the same monitor, in our default polarity, we select the even rows from in this case, it's the red left image, and the odd rows from the blue right image. There's a couple 3D modes. The first of which we use is the top-bottom configuration. In this configuration, the monitor or TV that is being output to needs to support a top-bottom configuration and needs to be set to that mode. And here's what an image might look like captured from our stereo camera setup. So in the top-bottom configuration, because we're stripping out half the rows and placing on top of each other, you get kind of a squished image on the top and bottom. This does, in these 3D videos, it does reduce your horizontal resolution in half. However, at 4K and even 1080p, it's still more than clear enough for most applications. And how all 3D monitors are able to display the images is by interlacing the two images together. So the reason we select different rows is because the final image is going to look something like this, where we're alternating the left and right images. The monitor and glasses itself are polarized differently so that the left lens only allows you to see in this case, the even rows on the monitor, and the right lens only allows you to see the odd rows on the monitor. And so that's how we get two separate images from the same display. In top-bottom mode, the monitor handles this interleaving, and the top-bottom mode just tells it where the cutoff is for the two different images. In row interleave mode, the 3D monitor can just display this image as it is, and with the polarized glasses and TV, it'll appear in 3D. So with the same image, here's what that looks like in a row interleave configuration. As you can see, in the vertical direction, there's not a lot of difference because our setup is set up to mimic human eyes. So your eyes don't really have a lot of vertical distance between them, but horizontally, it's just a slight difference. We set them 65 millimeters apart, which is the rough average of what a human interpupillary distance would be. So some of the challenges we ran into with this project is that our first constraint was that the product ideally needs to run in real time, especially for something like eye surgery or safety is a concern. Any latency and delay could obviously go pretty badly.
And so we chose NVIDIA Jetson devices for its CUDA cores and GPU processing because we knew we'd be doing a lot of video processing, especially with the interlacing operations. We have a lot of different components from different manufacturers. The SoC and development boards are from NVIDIA. The camera sensor, the IMX sensor is made by Sony, but the module itself is assembled by Leopard Imaging, as well as the adapter board and the drivers provider for Leopard Imaging. This gave us a lot of issues with dependencies and drivers working together correctly. Because of a lot of these issues, we've had to make pretty significant changes to the scope of our project. Primarily, despite a lot of troubleshooting and communication with Leopard Imaging and NVIDIA, we were ultimately unable to get 2 camera streams to be inputted into a single device. So we were not able to interlace the 2 camera streams on one device. And what we ended up doing is having 2 separate Jetson and Sony IMX sensor setups to record simultaneous stereo video. And would copy the video over to a single device for the interlacing process. So our video is pre-recorded, but the interlacing is done in real time. And Sunil's going to talk a little more about our hardware.
All right, so our hardware setup starts with our camera setup. It comes with 2 Sony IMX 334 cameras, which we chose for its cost and its ability. They're assembled by Leopard Imaging, and they're interfaced with MIPI-CSI2 to the cameras. And as Matt talked about, the 2 sensors are used to simulate the left and right eyes. Next, we have our capture devices, which is the NVIDIA Jetson TX1. These modules are designed for visual computing. They run Linux with the Jetpack software development kit. They come with a quad-core ARM Cortex-A57 microcontroller and a Maxwell GPU with 256 CUDA cores. Next, we have the NVIDIA Jetson Xavier, which is used for the row interleaving. Similar to the TX1s, they run Linux with the Jetpack SDK, and they output with either HDMI or DisplayPort, and we chose to use HDMI for its simplicity. And this comes with a 6-core NVIDIA Carmel CPU, or GPU, sorry, or CPU, sorry. And a Volta GPU with 384 CUDA cores. Next, we have our 3D monitor, which is interfaced with HDMI. And this is provided by Alcon, and this is capable of monoscopic input, top, bottom, and row interleave 3D modes. And lastly, we have our mode setting buttons, which we have 3D printed, and other miscellaneous parts and cables, which are listed. And here's our final setup. On the left, we have the image capture side, and on the right, we have the image output side.
All right, so now we'll talk about software for this project. So first, we take the 2 video inputs from the left and right eye camera. So we take the 2 video streams from the left and right cameras and read each stream to an array using libraries of CV. So once these streams are updated, we can processing them. So first we go apply the image correction onto them. For example, we have a CPM mode which has this foreground tone for the image, which allows like a surgeon to view it with the stereo of the eye better. We also have slight saturation value changes that you could do, which allows like the user to slightly change the color to match their own preferences. Then after that image correction step, we look at the display mode of the camera to see how to show it on the 3D monitor itself. You can choose left eye or right eye monoscopic, which essentially we just choose to show either the left frames or right frames. You can choose top, bottom, or row interleave. So as Matt described earlier, we pick the even rows of the left image and the right rows of the right images, and then combine it as shown previously. some 3D glasses or monitors that have the polarity swapped so that the left eye needs to see the on and right eye needs to see the even. So you can just choose to swap which one you pick off the images to do that. And additionally, dealing with 4K at video at 30 FPS takes a lot of processing power. So we use CUDA via a library called Pi to essentially help us speed up the process more time.
So as Sunil mentioned, we have a button controller which allows the user to change settings relative to the real-time running of the program. This button controller introduces with the Xavier via its onboard header and converts to the main programming via an interface software. So each button press will trigger interrupts that can change global variables. These global variables are checked at each iteration of the video output loop. So whenever a button is pressed, that change will be affected on the next frame. These buttons control the changes mentioned earlier. So things like through the 3D modes, swapping the polarity on and off, or like swap to default, and then toggling the CPM mode on and off. We also have the UI overlay that displays all the information to the program currently running. So things like the frame rate, resolution, the 3D mode, and clarity. This is written to each frame of the image and then output to the 3D monitor. Next up, we have a quick little demo video to show you about the running of our program.
Our program can be started from the command line. There are two required arguments. The first is the left camera video source, and second, of course, the right camera video source. We'll also set a couple optional settings. We'll start by doing just the left video source and in full 3D mode. Now, Thomas is going to go through some motions that demonstrate the depth of the stereo cameras. On the top left is the overlay that shows the current resolution, frame rate, 3D mode, and polarity. As you can see, it's currently showing just the left camera, and you use the arrow button, we can toggle to the next mode, which will show just the right camera. Next is the top bottom mode. Notice that in the default polarity, the left camera is on the bottom and the right camera is on top. We can swap the polarity with the arrow button such that the left camera is on top. In this configuration, the 3D monitor needs to be set to top bottom mode so that it knows to interlace the image before displaying. And finally, we have row interleave mode. In this mode, the 3D monitor does not need to do any additional processing as the interlaces have already been handled by our program. Yeah, so you can see, it's not a great demo in 2D because it just looks blurry, but on a 3D monitor, as you see, the closer you get to the camera, the greater that difference between the left and right eye, and that's what creates that effect of something coming toward your eyes. And so finally, we'd like to thank Alcon, as well as Yupei at Alcon, Professor Yoga, and our TAs, Bryce and Chris.
Yeah, I misunderstand. Didn't you say that the embedded software was Linux? And then in your video, you're turning things on to Windows script. Where is Windows?
That was just a little movie magic because when we recorded it, the screen was really big, and so in the final video, you couldn't really see anything that we were typing. So I just ran it on a test bench with the Windows machine.
I'm speculating here, but I imagine that the ophthalmologist sometimes may want to look directly into the lens, and sometimes they want to see the video. So all the two things combined, the camera is to pass through somehow into the lens.
No, they're not. So the camera replaces, Alcon's solution, the camera would replace the eyepiece because the microscope itself is not made by Alcon. They make the attachment to it. So if they wanted to look through the eyepiece, they would have to remove the camera and put the eyepiece back on. As far as I understand it, it's kind of just a latching mechanism, so it shouldn't shouldn't be too difficult to swap in and out.
How does the surgeon actually see it?
They'll be wearing these glasses. So they'll see them on the 3D model. They'll be wearing.
You can do some field tests to see, whether the surgeon might have a headache or something like that after a hour long or long surgery.
So essentially, I don't know if you know, about a few years ago, a lot of the companies touch 3D TVs and whatnot. So essentially, while we were working on these 3D videos ourselves, we had ours look at seeing whether or not the 3D video is working or not. I guess we didn't test on all users, always for us, we didn't receive anything, so I'm not looking for 3D glasses that follow ourselves videos. So it should probably be fine.
Yeah, I had it's an existing product, and so what our goal was to get rid of the host computer, which is that it's a really large box. It's basically like a couple $1,000 Windows gaming computer. So it's an existing product. So I'm not sure about whether or not surgeons get dizzy, but from what I can tell, if the frame rate's up to par, so at 4K 30 frames per second and either 1080p 60 frames per second, it shouldn't really cause any dizziness unless the person kind of has a propensity to be a little disoriented from 3D video. Yeah, you okay?
You guys have the monitor here so we can see what check out the TV.
Yeah, we'll bring it out to the posters.
Thank you.
So I'm just gonna do it. Okay, yes. I wanted to buy it. I think that's where you want to switch. You can play. Yeah. 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 You can go back. Three over here. Don't rely on. Yeah, we're gonna use that. And also make sure you speed the mic. Both and go forward. Okay, so hello everybody. I'm here to introduce you all to GEM. This is our geographical environmental module. Okay, so my name is Michael. I am project lead, and I mainly focused on writing software for GEM.
Good morning, everyone. I'm Adel Rivera. I also is responsible for software development.
Hello, everyone. My name is Larry, and I work on the PCB design for them.
My name is Rihanna. I'm also involved in PCB design, and I also work code for MATLAB, which will visualize our data.
I'm Sawyer Esquire. I mostly helped out with testing and debugging our products. So with current climate change conditions and global temperatures rising, wildfires are becoming more common and more of an issue. Last year in California, there were more than 8,000 wildfires and 2.6 million acres of land was destroyed. Another use case for our product is in an agricultural setting. So in the US, there are over 2 million farms, and within the last 10 years, about 100,000 of those were lost. So GEM can monitor environmental conditions and can be used to detect and predict wildfires, which can be especially useful in containing them if we can detect a fire in real time. And in an agricultural setting, we can monitor specific areas of farm to see if an area needs specific needs, and this can help increase crop yield.
Okay, so there are three different parts to GEM. The first part is our physical sensor node. This is a node that has multiple sensors that just collect data and monitor the environment. The second part is the transmission phase. This is where the nodes send the data to a single central receiver. And then lastly, in our processing stage, that single central receiver plots the data and presents it to the user. Okay, so this is what GEM looks like. As you can see, we have various different sensors, ranging from GPS all the way down to a soil moisture sensor. At the heart of the node, we have our STM32 microcontroller. This is based on the L0 family, meaning it's very low power, and it's ideal for our use case, since these nodes will be battery powered. Additionally, each node is equipped with a transmitter, and there will be 3 separate nodes that all connect to the single receiver.
The first two metrics we wanted to measure with GEM was temperature and humidity. And for the sensors we chose for this, we first chose the DS18B20 temperature sensor, external temperature sensor. We chose this sensor because it was waterproof and it has a long wire, so we're able to monitor the ground as well as temperatures outside of the module. For the second sensor we chose the DHT22 internal temperature and humidity sensor. Both of these sensors have a one-wire GPIO interface to communicate with a microcontroller, and they both have a programmable resolution.
So 2 other metrics we wanted to measure are light intensity and soil moisture. These are particularly useful in an agriculture setting to see how much sun or water specific areas are getting, and can also be used to tell how dry an area is for fire potential for fires. So we use this SparkFun soil moisture sensor, which just gets inserted to the ground and sends an analog value to the microprocessor, which is then converted using the data table in the datasheet. Next, we have the P-Cell2 photoresistor to get a reading on light intensity and how much sunlight an area gets. So this sensor needs to be calibrated, as it didn't come with its own lookup table. So we used a lux meter to get a base value in full sunlight, and then use that to create a conversion table. So both of these sensors use a shared ADC input on the microprocessor, and we use distinct channels to be able to switch between each one and read each sensor individually. And they are both corrosion resistant, so the modules can be deployed for a long time without needing any repairs.
All right, so another 2 sensors that we ended up choosing was a GPS sensor and a barometric pressure sensor. Starting off with the GPS, it is a PA10B thermatoproof. This sensor turns GPS and NVDA senses from which we parse longitude and latitude. It uses a UART interface, and the reason we introduced this sensor is because since a lot of the nodes will be split over a wide area, it's easier for the user to find out exactly where they're at. Next up is the BMP180 pressure sensor. It calculates barometric pressure and altitude, which is useful in determining high and low pressure systems because some crops need higher pressures and others lower. And this sensor is interfaced via I2C. Okay, so next up is the ESP32 lower line gateway. This is pretty much a 2-unit device. Starting off is it's the ESP32 microprocessor. It is a multi-network device and offers connectivity to Wi-Fi, Bluetooth, UART, I2C, and MPI. Together, it uses the RFM95 to access the lower frequency spectrum. Yeah, and it's a very low power tool.
Here's our PCB schematic. All the sensors previously shown in the presentation, all connected to the microcontroller here in the middle. Some important peripherals here shown are the temperature and humidity sensor, the water sensors here, and the GPS sensor here. Here's the layout of the PCB of all the connected units. Here's our assembled PCB. This is a 2-layer PCB board, and it has 90 times 100 millimeter design, and all the components are mounted on top via pinheads.
So while the first version works 100% functionally, for the second version, we're really trying to go beyond that by making it a little bit more compact and field testing ready. The first thing we did is integrated a power supply onto the board. On the left image, you can see there's a battery slot. On the right image, right next to the chip, you can see there's a cluster of chips responsible for voltage conversion. Basically, it can convert 9 volt power split into 5-volt and 3.3-volt for all the modules on board. And the second thing we did is to basically make it more compact by employing a 4-layer design instead of just 2 layers. It's approximately maybe around 50% smaller. And the third thing we did is really restructure the board to separate different things into different areas. Especially you can see at the bottom, we have around 30% of the area dedicated to sensor mounts. The idea is that while we're doing field testing, we can just directly insert the board into the soil from the bottom side. This way, well, you don't need any extra support structure for the board. They can just stand on its own.
Okay, so moving on to the transmission part of them. So I talked a little bit about the ESP32 LoRaWAN gambit. So this is essentially the wireless transmission protocol that we use. It's very low power and it has long range. And this is due to the low bandwidth that LoRa has offered. It's rated to around 10 kilometers if there's not a lot of interference coming. It's also low cost, cool, and standardized. There's a lot of good resources out there to be able to set this up yourself. Okay, so I'm specifically going to be talking about the transmitters here. So our LoRaWAN infrastructure has a transmitter at each node. So this would be essentially one gen node. From that, it reads the STM messages that is sent over UART. This is all the data characteristics that the sensors pick up. And then it pretty much packages it, gets it ready on the ESP32 part, and sends it out over LoRa 950 megahertz using the RFN95.
Okay, so on the receiver side of things, we have configured one of our ESP32s as a gateway. And when it is configured as such, it has the potential to establish connections to 12 different LoRa transmitters. When it's also configured as a gateway, it will read the data that is being sent by the transmitters. And so this is all possible using the LoRaNow library. This is a library that's very useful and makes programming the ESP32 very easily. And so there's a lot of built-in functions, some of which we decided to include in our own gateway. So just to name a few, one of the ones that we decided to use was this unique node identification feature. With this feature, the transmitters are assigned a unique address, which the receiver can use to distinguish between the different nodes. Another useful feature to have was the checksum feature. This is what we used to see if any of the data was corrupted during the LoRa transmission.
So the third part of our system is data processing. So the gateway is connected to a computer. The first thing we'll do is just read from the COM port to gather all the raw data. And all the raw data, that's known as measurements, they are sent through one single frame. So the second step we need to do is basically unpack them. Because they are stitched together through delimiters, we have to separate them by removing those delimiters and identify which number correspond to which measurement specifically. And the first step is basically plot and record. We have a MATLAB code ready to display a real-time plots to the user. In this way, users will be able to, say, detect any anomalies or anything unusual in real time. And we also store the data in a comma-separated value file for any further analysis in case the needs arise. Here's our sample plots. Each row represents one node. Now, right here we have 3 nodes. Each circle represents one data point. We set them to take a measurement once every 5 seconds, but this can be changed. It can be as short as, say, twice every second, or as long as, say, once every minute, according to the needs of our application.
And now we'll show you a demo video of a field test of 3 working gen nodes that are collecting data.
Okay, so that was just our little demo video. And we'd just like to send our special thanks to Professor Yoga, as well as our two TAs, Chris and Bryson. They were incredibly helpful. We definitely could not have done this without them. We'd also like to send our thanks to Laritech, as well as CACI and the College of Engineering. Thank you.
Your receiver can listen to 12 transmitters at the same time.
Yeah, so we got it from Sparkman and they rated it up to 12 devices. And also a cool thing for our mission is that any single one of them can be set up as either a transmitter or receiver. So it's kind of like a variable. Any one of those devices as a receiver, and each one is rated up to 12.
Okay, and could you run robin through more devices if you want to?
We never really tested more than that. I guess if we have multiple receivers, it picks up whichever 12 or anything.
How does the user go about deciding what type of sensor to deploy where?
So one gen node has the same amount of sensors with about different characteristics. So just the gateway receives all the data from every single individual sensor. So if you wanted to pick and choose sensors, I guess you could just remove, or maybe you could potentially find a way to add or disable.
So each node has all those different kind of sensors.
Yeah, so each single one has
Now,
all the
second
sensors.
part of the question is, okay, how many, given an area, how do you decide whether you need 50 sensors or 100 sensors?
So I guess that's more up to the user. Let's say you have a lot of acres and but you're only really interested in a certain area of the vegetation, then you could deploy these to see how the soil is, different features, like with the charts, the data gets saved to the leads. So future application we wanted to do is maybe machine learning algorithms from these CSV calls to show trends and let you know if it's active.
A question about your selection of vector control. That's a Vortex L4.
No, this is basically just the L0.
Oh, it is.
Yeah, so it's very low power.
Okay, I was gonna say, it seems like you've got a lot more horsepower than you need to sell. Okay, yes. The other question I had is, you think the battery life? What's this thing?
We haven't really tested it, but the way we operate the nodes is we take a measurement, say, according to your needs, of course. Right now, we've set them to take a measurement once every 5 seconds, but between them, the nodes are actually in sleep mode. So a very rough number, let's say in sleep mode, only the chip is running, so maybe the current is around, say, 20 milliamps plus, say, 3 volts. So that's like around 50 milliwatts. That's in sleep mode. And I don't think we need to care too much about the instance where we take measurement because that's just one instance.
And also to follow up on that question, we currently have 2,000 milliamps portable batteries, and they're easily able to take more than a day use.
Right, so the reason I asked the question is that a real system like this, you've been deploying nodes over a really, really wide area. And battery life is sort of the determining factor.
Yeah, so that's something that we wanted to further look into. On our second version, we had like the battery tray. I don't know if you remember that. So that's like something we can also add on. We also got solar cells to maybe try to find a way to retest batteries over time.
Yeah.
Let's see if it works.
Give it a test.
Yeah, the clicker's not working that great right now.
All right, no, I'll just point to you when I need you to
Okay.
push that.
Yeah, it's too.
Yeah,
Or
for the PCB only. though.
Because Spencer Gregor used to want to
Both mics?
No, I'll
Yeah,
just
both
point to
work.
you.
Make sure you guys hold them towards you and kind of close.
Okay.
I mean, we should be speaking.
Ready? Watch change slide. Yeah.
Hi everyone, we're the Critter Group, and good. Hi everybody, we're the Critter Group, and we're working with Capstone medical system right here in Toledo, California. So, before we get started, just like to introduce ourselves and the team behind the wonderful project.
I'm Noah. I'm the project leader. I worked on the mobile app as well as Bluetooth.
My name is Moises, and I focus on 3D design.
My name is Shrika, I work in the real-time software system.
Jimmy, I worked on PCB and LEDs.
I'm Alex, and I worked on Bluetooth and data processing.
Better understand products, it's important to talk about coagulopathy and other products. Coagulopathy is referred to any of a myriad of pathologies relating to abnormalities in the way of patients' clot or prevent bleeding. There are many different types of coagulopathy. Some more well-known ones are deep vein thrombosis and hemophilia. Now, it's important that doctors and patients understand the risks involved so they can better reduce the possibility of internal bleeding or excessive clotting. One case that we're particularly interested in is the case of physical trauma patients. In some cases of physical trauma, the patient can develop a life-threatening disorder where the blood suddenly stops clotting properly. In up to 30% of cases of trauma-induced coagulopathy, a patient can die within the first hour, making it absolutely vital to get this information quickly and accessibly. So with that in mind, we had certain goals we wanted to hit in the project. One, we wanted to monitor fibrinogen. Fibrinogen is a protein produced by the liver that circulates through the bloodstream and can explain the clotting activity of the patient. Doctors use this information so that they can better see what's going on in the patient and how their body is reacting to different medications. On top of that, we also wanted to make sure that our device was fast and portable. The current state of medical technology being what it is, the devices that are currently used to monitor fibrinogen are extremely expensive, extremely large, and extremely stationary. Also, they can take up to an hour to properly produce a test. We found this to be completely unacceptable. Another thing to keep in mind is that the samples that are used to give these measurements are extremely susceptible to degradation. So we wanted to ensure that doctors can trust that they have the highest quality samples when they're doing these tests. As you can see, this is an example of one of those desktop machines. They are not meant to be used in the field, and that can be a serious problem. Another thing we wanted to keep in mind is we wanted to make sure that our system could properly slide into a hospital's current data management system. By using a cloud implementation, we were able to ensure that doctors can trust that they have the most current and up-to-date information on their patients. On top of that, we wanted to ensure that all healthcare staff can see real-time changes to their patients and what's going on with them. This can be extremely helpful in a lot of situations. One case that is really important is the case of mass casualty events. In one of these tragic events, paramedics are often battling each other, trying to figure out, who's got this patient, what's going on. They can step on each other's toes. We want to ensure that paramedics can work together and see all of their patients over time and what's going on with them. So with all of that in mind, we devised our CUDA reader.
So we had something to work with at the beginning. So thanks to Aptitude, they developed a rapid COVID test that used a microcontroller that interfaced with the Raspberry Pi Zero. And so what we had to do is take the fibrinogen and COVID test that Aptitude had and implement it to one simple device. And then while changing the device, we also had to change the existing case. And we also used, we provided a platform, which is a mobile app that would manage devices, patients, and test results. And so a little bit about the CUDA reader device. It was adapted from the ACE reader that was first developed by Aptitude. And then what Aptitude did was they used the COVID test with saliva samples and gave you results in minutes. And then our mobile app was used just as a mass management system. And then we had to develop the fibrinogen test that did the test in just less than under a minute.
Okay, now I'm going to go over some of the key components. There are 3 circuit boards in our implementation. In the blue, you'll see the main PCB. This is what we adapted from Aptitude's work. We made 2 notable changes. The first one is we added a PWM driver. The driver allows us to control the LEDs with a little more flexibility. The RTC module allows us to synchronize the time of the Raspberry Pi. That's not a feature that it comes with by default. The Raspberry Pi Zero W is another key component. It has its own circuit board. You'll see it in green. It's equipped with Wi-Fi and Bluetooth, as well as GPIO ports that allow us to communicate with the other devices. The protocols that they use for communication are along the arrows there. Uses I2C, UART, and then 5 volts for power. And then the last breakout board is a tiny guy. It's an LED breakout board that just communicates the status of the device with the user.
All right. So the Raspberry Pi Zero W is the brains of our operation. It is a mini computer that supports UART, I2C, and SPI. It also runs Wi-Fi and BLE, Bluetooth Low Energy. It runs a combination of Linux and Python libraries to support our reader and get our fibrinogen results.
And then we use the microcontroller, and the microcontroller was used to emulate a potentiostat, which in short is used to perform electrochemical measurements.
We also added the real-time clock. Like I mentioned earlier, time data is extremely important to us, and we want to use this in theory. So by using a real-time clock, we can ensure that during boot cycles, we still have up-to-date time.
And finally, we have this PWM driver, which is used to control the LED breakout board. And the LEDs used for statuses and decibels. Besides being a visual upgrade due to the increased control over the brightness of the LEDs, the PWM driver allows us to create more statuses and have more flexibility as Aptitude plans to implement more tests using software. And here's our schematic, or this part of it. In the middle, we have the Raspberry Pi connected to most other things. On the bottom, we have the RTC and its battery for when the device is unpowered. And on the side, we have the PWM driver and this connector, which allows the PWM driver to connect the ribbon cable to the LED breakout board. Here's our PCB, once again adapted from Aptitude's ACE reader. Chips are inserted on the left here in this gray part, which is the heating element that is used for COVID tests. Cool features. The RTC is up at the top here. Raspberry Pi actually sits on top of the main PCB. There's more components underneath. And then the PWM and LED board connector down the bottom here. And on the back, similar situation. We have the RTC battery holder that's didn't fit on the front. You can also see it into the Raspberry Pi.
To communicate between the Raspberry Pi and the mobile app, we decided to use Bluetooth Low Energy, BLE. The Raspberry Pi will act as a BLE server and send any test status or results to the mobile app, which acts as a BLE client. For changes to the real-time clock in PWM, we added a real-time clock because we needed accurate timestamps. So time is pulled from the real-time clock between Raspberry Pi boots. For the PWM, instead of hooking up GPIO pins to the LED breakout board, we decided to use a PWM driver. So this allows greater control of the LEDs for indicating more test results. Now for a device workflow, the test begins when the chip is inserted, and the chip type will be automatically detected. So right now, we support COVID and fibrinogen tests. And different procedures will be run for each test. While some of these procedures may be shared by both tests, there will be different parameters and sequences done for each test. And finally, the mobile app will receive any error messages or test results through Bluetooth Low Energy.
Now I'm going to go over the mobile app really quickly. The key feature of the mobile app is to monitor the reader devices. That's kind of the core functionality. Everything else is kind of extra. It uses Bluetooth Low Energy to communicate with the reader devices, and it can manage several of those connections at once. And it's actually just limited by the Raspberry Pi Zero W, which supports around 10 at a time, as well as the Bluetooth chip on the phone that you're using. It allows for authentication and storage on the cloud. One important note here is that this project deals with medical data. None of our data at the moment is encrypted. That's something that we would definitely do if we had more time. This system, this app opens up to this page here. This is a monitoring page. You'll see the devices appear as cards. We tried to make it really easy to understand what was going on each device, so you can monitor several at once. This is what one will look like when it just finishes the test. The header turns green. You can see the selected patient, which is me, and you'll see the result just under that. When this test finished, this is just an image, so you can't see it, but a notification was generated on the phone. And that's nice because if you wanted to run a test and that was minimized, or say you're on a different page of the app, it would send you a notification with all of your results. This shows some of our authentication features. You can sign in with Apple or Google if you already have one of those. Or if you'd like, you can register an email and password account. If you forget your password, you can use the password reset link. And this is an extra feature we added with situations like mass casualties in mind. So if you had several people with reader devices monitoring a large number of patients, it is very nice if you can synchronize all of the information that multiple people are measuring and have it in one nice interface that's got every patient's information. And to do that, all you have to do is open the organization page, choose a name for your organization and add code. And anybody else with the app can open it up, put the add code in, and all of your data is synchronized.
So before we show a quick demo video.
Oh, sorry, got one more quick slide for you. When you've actually collected some data, you'll see this page here. You'll see I've selected fibrinogen as the test type, so you'll see the fibrinogen concentration of the sample change over time. This is what it would look like if something terrible happened to somebody and then just about an hour they got better.
All right, so yeah, before we show you a quick demo video, we just want to point out that we didn't add any, blood, it's a biohazard, but we would be inserting it into the collector on.
Step 1. Connect the reader to power. As shown, we connected via power. As we wait, please add the blue solution into the test tube by pressing both caps firmly. As we wait for the reader to boot up, we know it began when the light flow begins. Now the device is ready, so the white light shows, and we're able to open the app and connect to the reader. We will now insert the chip into the reader. The reader will now begin starting a new test, as shown on the left hand side. When it is ready, we now add the test tube into the chip. Make sure to press firmly. During this time, we wait for the fluid to fill into the chip. When the test begins, the app will notify you that the test is ready. After the test is done, we know it is ready when we have a notification pop up with our.
After the results are uploaded, we're able to click on the bottom right button and view the results of any test done to a patient over time.
Real quickly, just like this thing, Tyler and Zach were here today along with Clay and Wental, the rest of the SDF team, as well as our wonderful peers, President Chris and Professor Ray. You can ask
Keep and the test tools identical for a COVID test.
So, yeah, so they are slightly different. Basically, you'll notice that there were three parts to that. There was a blue solvent, in the main collector, they can insert in fluid, and then finally the chip is inserted into the. Now those chips are slightly different. The COVID test and the hybridity test use slightly different modifications. We can support up to 8 different tests using our current system, and that's how we're able to automatically detect which test.
But it's different because they have
Basically,
an
we've got-
ID that says the test is different. Or
Exactly. Basically, we've got 2 different needs. So we need to use the on-off bit. So we've got 8 possibilities.
Just technology. Sounds like
Exactly.
technology there.
What are the performance criteria for the system? And how do you know that you've succeeded?
Yeah, so definitely. For fibrinogen, which is our main goal here, we have, we were mainly responsible just for the device. The active team has coordinated with multiple doctors and health professionals to verify that the system properly works. With a little bit more time, we would love to go in and actually test, different blood and compare it to the existing devices to see how accurate our system is in that sense. The main characteristic that we were really focused on is the time. So, like you mentioned, it takes about an hour with the current systems. Our system takes exactly 1 minute.
Got a question, earlier on in the presentation, you showed a standalone microcontroller. What precisely does that microcontroller? It looked from your presentation like all the processes happening, right?
That microcontroller is used to actually send voltages through the symbols to actually run the electrochemical measurements. It's this microcontroller designed as Eco, which is loaded.
It's a commercial based.
Okay, no, that's continue. But so, did you have to do any software development in that microcontroller, or is it all? It's all library based.
That's not library based. The aptitude team reverse engineered the unset Eco, and they use that to train my.
Okay. So all the software development was essentially in Python.
Exactly.
On the Raspberry Pi.
Exactly.
Hi, everyone. This is our project Airabot. Let's begin. I'm Eric Buckland. I'm the project lead. I did the UGV and remote station, hardware, software design, and integration.
I'm Angela. I work on the Nordic board development and PCB design.
Hi, I'm Kim. I'm in charge of the Nordic board development and the communication protocol.
Hi, I'm Tom. I work on the Nordic board development and as well as
And we would like to give a big thanks to Phil and Tiziano from Air Environment. and Yoga, Chris, and Bryson from UCSB.
So in this project, we are creating a system that will provide stable communication to an unmanned ground vehicle in disruptive environments. And we are doing this because when a UGV enters such environments, problems such as lost connections become more commonplace. And the solution we are exploring is ultra-wide bandwidth communication. And this communication will be ongoing between relay nodes that will be deployed by the robot. To go into a little bit more detail, on the robot, there will be a LiDAR module as well as a camera module, and the LiDAR will perform Hector SLAM and create a mapping of the room. And both this mapping as well as the camera feed will be sent back to the remote station. On board the nodes that will be deployed, there will be UWB antennas as well as a proximity infrared sensor to detect nearby motion. And as stated before, our goal is fast and reliable communication with the UGV. So what is ultra-wide bandwidth? It is RF communication that uses narrow impulses as opposed to sinusoids. Its frequency range is 3.1 gigahertz to 10.6 gigahertz. And as its name suggests, the minimum channel bandwidth is 500 megahertz to 1.3 gigahertz. And this is as opposed to other channel bandwidths, which is typically 20 megahertz. And so why is this so important? Well, first of all, ultra-wide bandwidth is very low power and operates near the noise floor. The FCC regulates that the power spectral density of ultra-wide bandwidth is negative 41.3 decibel meters per megahertz, which is extremely low. It is resistant to multipath interference. And if you look to the figure on the right, you'll see the impulse juts out from the noise and easily reaches a threshold, which is very good. Because the frequency range is so large, it is easy to choose frequencies that avoids frequencies with lots of ongoing communication, such as 2.4 gigahertz or 5 gigahertz with Bluetooth and Wi-Fi. And it achieves data rates up to 27 megabits per second.
And here is our outline of how we solved our problem statement. We have an unmanned ground vehicle in the field, which has a camera feed, a LiDAR mapping, it's remote controlled, and has a physical node deployment.
And our nodes are deployed from the robot, and we created a chain topology to link the unmanned ground vehicle and our remote station. For each node, there is a proximity infrared sensor attached, and the node is powered by an external battery.
And on the remote station, we have a camera display of the UGV's camera. We have two different LiDAR map displays, one of the local map and one of the full map. We have a node data display displaying the PIR data of each node, and we have analog control with the controller. Here's our block diagram of the UGV. We have an NVIDIA Jetson TX2 running ROS. It's connected to a camera and a LiDAR with the algorithm Hector SLAM. It's connected to a node launch servo controller, a drive controller, and the Nordic device, which has an attached Qorvo DWM module. Here's our robot, and you can see our camera module with the LiDAR on the top and the node deployment mechanism on the right.
So a node consists of three parts: a Nordic NRF5840 microcontroller unit, a passive infrared sensor for the object detection, and a Qorvo DWM, a radio frequency module that handles the UWB message transmission. Once the proximity sensor detects something, it will tell the microcontroller unit and trigger a message transmission event on our DWM module. We have a sequence of such nodes, and the nodes will be communicating with each other under this ultra-wide bandwidth signals provided by the DWM module.
And on the remote station, we have a laptop running ROS, very similar to how it runs in the UGV. It's connected to an image process which decompresses the images received from the UGV. It also is connected to remote control and the Nordic SoC with the Qorvo DWM. And here's our block diagram together. You can see that all the processes have the Qorvo DWM in order to connect to each other. Here's our system in the field. You can see that we have all of our systems connected together in a chain. And here's a view of our remote station. On the left, we have all of our node data information, including which nodes have been triggered with the PIR sensor and our control data that's sent to the robot. On the bottom, we have the camera view of the robot, and on the top, we have the local map around the robot from the LiDAR. And on the right, we have the full map that the robot has generated over the time that's running. It also displays where it's deployed the nodes. And now we'd like to show you our project video. It should give you a better idea of how our robot functions in the field.
This is the final version of our printed circuit board. Before having that design, we were using the Nordic development kit. And in order to interface with the DWM module, we had to stack another evaluation board on the top of the Nordic board, which makes our node quite bulky. So in order to make it portable, we designed our own printed circuit board. This board is a 4-layer board of size 2.5 by 2.5 inches. It is developed based on the Nordic development kit. We removed a bunch of unnecessary components and we integrated the DWM radio frequency module on board. During the design phase, we experienced some shortage of the components, so we made some hardware modifications, and it's worth to mention that our board actually worked in the first iteration. This white little chip is the DWM 3000 module, the radio frequency module. It is 0.4 by 0.9 inches. Half of it sticks out of the board, and that's the antenna part. It can operate under low power, and it achieves up to a precision of 10 centimeters regarding location mapping. There are 2 different channels, and it supports a data rate up to 6.8 megabits per second. It is released in 2020, which is quite recently, and we had some difficulties finding the documentation and the source code of that. As previously mentioned, the ultra-wide bandwidth technology is gaining its popularity, combining its feature of low power and high reliability. That's why we are using this.
And for this project, we built our innovation protocol from the ground up, mainly for these reasons. First, the deployed module doesn't have any pre-built communication structures for large data in complex communication networks. And also it doesn't support dual channel communication, meaning that it cannot send. And also without redundancies and a protocol, the communication is subjected to interference collisions with data logs. So right here, we have 4 horizontal lines indicating 4 nodes. And one possible scenario is that the node 1 is the node on the UGB, and the node 4 is the node on the laptop. And it's the UGB is trying to transmit a camera image to the laptop. So first, the node 1 on the UGB will send the first frame of data to node 2. Upon receiving that frame of data, node 2 will send a acknowledgement at 1 back to node 1, indicating that it has successfully received that frame of data. And then node 2 will proceed to propagate that frame of data to node 3. And after it received a act 1 from node 3, it will proceed to send a act 2 back to node 1, indicating that it is ready for the next frame of data transmission. And the same process will continue. The node 1 will send the second data frame. Node 2 will send back another act 1 while waiting for the act 2 from node 3. So basically, the act 1 is indicating that it has successfully received the frame, and node 2 is indicating it's ready for the next transmission. And should should act 1 be missing, the previous node will retransmit the data frame. And if the act 2 is missing, then it will simply wait until it receives another act 2 to transmit the next frame of data. And so this is our complete communication protocol with 2 data frames. And node 1 and 4 are the endpost nodes with their unique functionality, and 2 and 3 are the intermediate nodes with the same code and function that can, in theory, be infinitely many in our communication network. And to connect our double app protocol with our UGB and laptop, we also need a serial interface. So this basically, right here, the 3 middle nodes are the intermediate nodes whose functionality is purely the double app protocol. And the node on the UGB and the laptop would also have to interact with both the double app and the serial interface. Basically, if the node receives something through serial, it will send through deploy the double app protocol. If it receives something in deploy, it will send through serial again. And it also takes care of the communication directions should they change.
As Tom has explained earlier, the UWB is wireless and half duplex, therefore it cannot transmit and receive data at the same time. So this created a need to coordinate the nodes transmission and reception phases.
Also, there's a speed versus reliability trade-off that mainly concerns our double app protocol, comparing to, let's say, a simple linear propagation with no acknowledgements. The double app protocol ensures reliability at the cost of consuming more time, mainly in switching between receiving and transmitting the data frames and the acknowledgements.
The ROS implementation on both the UGB and remote station was also a challenge. We need to work with the confines of the decawave module and the limitations of our data rate. So we had to have very high compression between the 2 stations. We'll take a look at that now. On the remote station, we have the enjoy controller split into 2 commands, deployment and movement. We then have the deployment and movement command sent to the Nordic over serial. We receive back over serial 3 different types of images, the full map, camera view, and the local map. And we receive the compressed image from the robot, and we send the control data to the robot. And on the robot, we have the USB cam compressing the image. We have the LiDAR scanning the data, filtering the data, mapping it onto a vector map, moving it into an image, and then rendering it on command. We have an output of 3 different types of images. To the Nordic device over serial, we have the image from the camera, we have the map image from full, and the tile image. And of course, we receive back the control from the remote station, the deployment and movement, and this is an indication to send back the transfer. You can see we have the control data sent in over serial, and we have the compressed image sent out over serial. And this is what our system looks like altogether.
In terms of future applications, one part of our project was data transfer. So one of the ongoing research is multi-band OFDM for UWB, and the IEEE states that with multi-band OFDM, it supports data rates up to 480 megabits per second, and with multi-level modulation schemes, it can reach the gigabits per second range. In terms of security, 802.15.4z expands on the cryptographic options for UWB, as well as better defining the fine secure ranging for UWB. UWB has a low probability of detection and interception. This is because it operates near the noise band, as well as using accurate time of flight measurements to stop relay attacks. And that is the end of our presentation.
Great, let's take a Q&A.
The modules need to be positioned on their side, be vertically.
Yes. The module has to be positioned upright such that the UWB antenna and the PIR sensor are both facing up. Otherwise, a sideways positioning could affect the performance of both the PIR sensor and the UWB module.
And that's why we have the node slide in order to position them vertically, specifically designed so that they land on their feet.
In terms of the vehicle, you have the release mechanism, you have the camera, like are there any parts of the vehicle that you had to configure yourself, or were these all built-in capabilities?
We had to integrate serial interfaces in order to interact with them. However, with the LiDAR, we had to, it came built in with the Hector SLAM, where it came built in as a scan module, but we had to build the Hector SLAM algorithm into it, and we had to integrate everything together. Yes, the deployment mechanism was designed by me. Yeah, yes.
What kind of compression was used?
Yeah, so we used very, very high compression. We initially scaled the compressed images, the camera images down to very small images, and then we compress them over JPEG. Then we remove the ROS data so that we only have the unsigned int arrays for the images. And then we serialize these messages so that they can be sent on the network, and then deserialize, decompress, and then add on the ROS data afterwards.
How did you decide to use this particular kind of robot? Because it seems the type of terrain that it can explore is kind of limited if it's rolling.
Yeah, so it's meant to be rolling inside of a building. That's our intended environment. We initially had, this is our initial robot that we were given from the previous Capstone group, so we had to work within our project limitations, but it is quite versatile. The wheels are quite big and it's able to go over a fair bit of terrain.
Did you give any thoughts to possible abuses of such a system? I remember in the news there was the Roomba, the vacuum cleaner, was collecting data on people's houses that
Since our sponsor is a military contractor, the description we were given is that this project can be used for reconnaissance and is meant to be deployed in a unknown terrain and then left there.
If price was not a problem, why would you not put the sensors all around? So even if it drops and falls, why was the rectangle not spoiled?
Sorry, what do you mean by that?
If cost was not a problem, and you could use multiple sensors on your rectangular module, would you make it square or a cube? You know what I'm saying? Like
Oh, yeah, I see what you're saying.
Like a ball.
Yeah, so you're saying in order to make it stand on its feet more efficient? Yeah, so we designed it as small as possible so that it's out of the way of vision, and also so that it's stackable. We can have fit as many nodes as we can on the robot. The box around the PCB fits it exactly, including the AA batteries and the PIR sensor. It's a very tight fit. We're good.
Hello, everyone. Our group is ADA, or the Acoustic Detection Array, and what we've built for this project is a high impulse sound locator. Here's a quick introduction to the team. My name is Matt, and I worked on some GPS interfacing and full system setup.
I'm Aiden. I worked on the multiple iteration code, LoRa interfacing, and responsible for some of the graphic design on the project.
I'm Rafael, and I worked on the PC design and hardware interfacing.
I'm Kevin, and I worked on the audio processing and LoRa interfacing.
I'm Venkat, and I worked on the hardware interfacing and PCB design.
So I'm just going to give you a quick project overview of what we're doing. So what we're doing here is we're going to implement a network of microphones that uses a triangulation method to locate the origin of a high impulse sound. Some examples of these high impulse sounds could include like gunshots or explosions. And then the reason that we would want to locate a sound like this is in the prevention of things like blast fishing or poaching and other kind of illegal things like this.
So for a quick system overview, we have a system that has a minimum of 3 nodes for the multilateration algorithm to work properly. Additional nodes will increase accuracy and reduce error. And then on each node has a microcontroller that processes the microphone data in order to detect the high impulse sound. And once these sounds are detected, each node will send its location, the audio data, as well as the timestamp over to the receiver, which will then forward that data into a laptop, where then the central computer will use correlation techniques to determine the time differences between the sounds and multilateration to find the original source of the sound. And a closer look at each one of these nodes, we have an STM32 microcontroller which communicates with each of the peripherals. We'll sample the audio data from the microphone, communicate with the GPS to get the location and timestamp signals, and then send that data over to the LoRa transceiver to forward that data over. And then our microphone is standard 20 hertz to 20 kilohertz range microphone, and the GPS module is standard.
So for this project, we had to choose a microcontroller that would be capable of doing audio processing on board if we need to. So we chose the STM32F4 family because it has a lot of powerful microcontrollers. And our microcontroller is 144 LQFP. And this is kind of nice because we're able to hand assemble a PCB, although it's a little bit difficult. And it's a 512 kilobyte flash and it has 128 kilobytes of RAM, which gives us a lot of space to store large buffers and programs. As well as it has a 180 megahertz clock, which operates really quickly for filters and other types of embedded signal processing that we have to do. And of course, because there's a semiconductor shortage, it's really important that it's in stock and
So the GPS module we're using for our project is just a generic GTU7 model. What we're doing with it is we're going to receive location data and also a PPS signal, which is a pulse per second data each second. We're going to get the data through UART. And then with the PPS signal, we are going to use it to synchronize the clocks on each of the nodes so that they are all synced to each other. And the clocks that we're using have up to 90 megahertz of precision.
So for this project, we chose the INMP 441 microphone because it's omnidirectional and we can receive impulses from all directions. In addition, it interfaces to the STM32 over I2 audio protocol, and it's able to have a 24-bit output, which allows us for audio, precise audio data, as well as a 48 kilohertz sample rate for the clock, and it has an LR pin, so you can have a microphone for both the left channel and right channel. And finally, we added a windscreen to it to prevent false positive detections due to wind and other types of noises, and this should help with that.
For a LoRa module, we use the Semtex FX1276 transceiver, which is on this little breakout board. The reason we use LoRa is because it's long range and power efficient, and it was ideal for our application. We interface with this device with the microcontroller using SPI, and the range is ideal for our purposes, 1 to 2 kilometers, depending on the terrain. And then with that, we use it to just ping the audio data and timestamps along with the location, sending it over to a central. Putting it all together, here we have the full system overview. We have 3 or more nodes wirelessly transmitting data over to a receiver node, which is a bare bone version of our regular nodes, but simply just the transceiver microcontroller. All that data is then forwarded to a laptop, and below we have a blown up view of each individual node, again with the microcontroller and its brick.
So here's the PCB schematic. As you can see on the top right, this takes the majority of the actual schematic itself, and that's the microcontroller. Because we have 144 pins, we're able to have a lot of flexibility in how we connect all the connections. We're able to break out SPI, timers, UART, and the rest of it is just power delivery. Here's how it all comes together here. In the center, you see we have a microcontroller, and on the top right and the bottom left is where microphones go. The bottom right is where the GPS is, and the top left is where the LoRa transceiver is. The reason we went and organized it this way is because the microphone modules and the LoRa module, we can quickly replace them in case they're not performing the way we need them to. Here's what it looks like in the end. We really liked it because it has 4 layers. Obviously, all of them were hand assembled, and it worked on the first try. We're very relieved to hear that. And additionally, it's very small. It fits in my pocket and on my hand, so we're able to, when it's deployed in the field, it won't take much space. And again, here's final products.
So in this project, we're using LoRa, which has low bandwidth. So it's really important that we don't send all the audio data continuously because it's difficult to stream, and we only send the impulse itself. So we have to implement impulse detection on the embedded system. And one of the problems with this is there's a lot of background noise, like when people talking and so forth, that can trigger the nodes. So it's hard to use a raw threshold and just cross that threshold to send the data over. So to improve this, we did filtering, where we filtered for a specific impulse frequency. So our impulse was a wood impulse, basically putting 2 wood pieces together. And here are 2 graphs, one of the unfiltered version, the filtered version. And after filtering, you can see that a lot of the kind of other noises are removed and kind of focused only on our specific impulse. And now we can use the threshold technique to easily kind of like detect the impulse without getting false positives. So for the multilateration algorithm, we had to calculate the time difference of arrival between the nodes. So for this, we could use the raw timestamp from the GPS module, but this isn't very precise. So instead we use cross correlation, where we check the similarity between 2 pairs of signals for each one of the pairs. And once we do that, we check the basically time difference between the peaks of the cross correlation output, and to get that gives us a much more precise time difference of arrival calculation.
So now that we have all of this data about our time differences of arrival, we need to analyze them to generate our prediction about where the sound originated. Unfortunately for us, this is not as trivial as it might at first seem, because we do not have the distance between the true location and each node. We only have the relative distances between nodes from one to each other. This means instead of using traditional triangulation methods, we must use multilateration instead. Multilateration is a system of equations that allows you to based on the time difference arrival between two nodes, generate a set of solutions that are predictions for where the possible source could be. By having at least 3 nodes to generate a system of equations in this manner, you can reduce the number of possible solutions down to a single point. Unfortunately, in the real world, it will not be quite a single point because of all the things introduced like noise and time error in the real world. So we can oversolve our equation by having more than just the bare minimum of 3 nodes. We implement this on our software side at our central computer using the SymPy and SciPy libraries for Python. We use SymPy to generate a combination equation for every pair of nodes in our system. And then we can use SciPy to create a least squares regression to generate our prediction properly. Here's an example of some of the testing we did. Our initial testing was done at Gersh Park in Goleta. As you can see by this diagram here, even with the bare minimum of 3 nodes, our results tend to be fairly accurate, at least on the scale of an array. And even though this is a public park with large amounts of background noise, our system is able to correctly filter out just the frequencies and the sound profiles we were looking for to generate an accurate prediction. This is another test result we had at a different location, again in a public place with lots of background noise. You can see we added an additional node for this test, so there are 4. And as described earlier, adding additional nodes will usually increase the accuracy of our tests. And now I'll hand it over to show a demonstration of one of our tests in action.
Hello, everyone. We are currently at Ellis Park in Santa Barbara, running a test for our audit. Our test setup consists of 4 nodes and a sound source. Our 4 nodes are set up in this configuration. We have 1 over here. Our second node is over here. Our third node is over there. And then our fourth and final node is set up over there. Okay. How the check works is we have each node currently in a listening state, waiting to hear some sort of loud impulse sound. And there's even a birthday party going on over there. Random voice, they're specifically designed to only look for on-time impulse audio noises. Our base station is set up over there, and once all the nodes receive the audio data, we'll send it to that computer for post processing. And now we will begin the test with our input center. Okay, now we are swapping to the computer side. We are currently running a Python script where we gather all of the data from each of the nodes and then store it in text files that we put into a multilateration algorithm to find the location. So we have first we have the tree sound, which is our actual location. Now node 1 has just sent this data, and that is GPS value for node 1. Node 2 has also just sent this data. So each node has received the sound and is waiting for its time slot to send the data. That's why they are coming one by one. Node 3 has just sent it, and we're just waiting on node 4. And once that happens, we will see it to the customer, which is right here. So we have the true sound in red, the predicted sound in blue, and then the numbers are the locations of each of the nodes. So we also calculate an error distance based on that, which is 2.6 meters, which is very small relative to the error given by the GPS standard. So we can conclude that this test is very successful.
So after collecting our data from all of our files in different locations, different environments with different setups, this is a histogram of our error between our predicted sound origin and the actual sound origin in meters. This distribution is skewed right, which is really good for us. And a lot of the error, if not most of it, is under 4 meters, which is the same amount of error, the average amount of error given from our GPS measurements. So anything under 4 meters is ideal for us, and very rarely does it go above 6.
So now on the power consumption side of things, we just use the USB power meter to measure how much current it was drawing. We noticed that in this mode, it would draw about 110 milliamps of current, and then while it's actively transferring data, it needs about 120 milliamps. This is actually very good for us because we looked at the power usage while it's sending data, it's about 1.1 watts. And when we compare that to like the solar panel, most solar panels will output about 5 watts of power. So they should be able to power our device for a long period of time. Once it's put in the field, it should be able to just keep the same operation as long as they would get power from the sun. So when we designed this, we were kind of trying to make it low cost so it would be practical. So the total cost of this system or single node is $46.44. And this will be produced at a low volume, but obviously if you go to mass production, this cost will reduce by about 10 to 30%. So this makes it really practical to actually continue to use the field. So in order to conclude, we were able to successfully design the node and handle single and they all work fine. And what we really liked was how accurate the system was. So the standard error for GPS is about 4 meters. Most of our tests were below 4 meters. So we think that they're successful. Additionally, we made it work with minimum 3 nodes, but increasing it more than that is very easy when you just change the parameter and you're able to go as many nodes as you want to. Additionally, right now we're detecting sounds with a wood block that is about 50 meters from the notes. We compared the loudness of the wood block to the loudness of much louder, like an explosion or a gunshot. And due to the way the sound behaves for distance, we estimate that we should be able to still detect the sound of gunshot or explosion up to about a kilometer away.
Now we just want to give some thanks to people who helped us out during our project. First, we want to thank our professor, Yogananda Sukapali, for his knowledge and advice throughout this entire year. We want to thank our TAs, Bryson and Chris, for the work that they've done with us. And then we wanted to thank our sponsor, CACI, for their funding and guidance, and specifically a few people there who have taken time out of their work week to help us. Austin, Eric, Jeff, John, and James, and a few of them are over there. Thank you guys for coming out and helping us. And yeah, that's it. Any questions?
How would you characterize the sound? Feel that to affect the two laws. How was it defined? Like what is the data structure that defines this sound?
Sure. So we just had an array of int16 int16 values, so basically 2 bytes. The output of the audio is 24-bit chunks, but we were only using 16 bits because we didn't need more precision than that.
We were filtering for frequency is I think the answer to the question.
Right. So if you were to look at gunshot.
Yeah, so you have to do a little bit of analysis on the sound you're attempting to detect. In our case, it was this wood block, which makes a certain set of frequencies. A gunshot would make a different set of frequencies. And you can collect data on what type of sound profile you're looking for to pick that out from background noise.
Basically, we're using FAR filter. So you can have like an array of like coefficients to the filter, which will be the taps that we're filtering for. So first we like analyze like a raw waveform in MATLAB. We look at the FFT of that, see what frequencies we cared about, and then like we make an FAR filter for that and input those taps into
the UI call. Like you record it.
Yeah.
It's experimental. You could allow your questions or requests.
Yes.
I had a couple slides earlier. You had a bill of materials and cost estimate. I'm curious where you're getting PCB fab and assembly for $2.
Us.
So you did. We have a board as well.
Yeah.
Yeah.
So I got it. Okay.
All in-house.
Actually, the thing is like that number is actually calculated based on like a fab house. Because the thing is like when you get a fab board back, it's not like you get one board, it's analyzed like first of boards, right? Typically. So when you actually and we were getting it from like PCB JLC-PCB in China, so we actually like divide the boards up. It comes out to like a really reasonable cost. Like JLC-PCB is actually like most of the things are like the shipping cost is actually more than like the board itself.
That's a great deal.
And we're also using like a kind of board with like typical like we're not having like some super small like traces or like some like super like exclusive things. So we follow like fairly standard like protocols. So it's not important.
Yes.
And then you said there was like a low error, like 4 meters. So that's from 3 nodes. So did you find like with more nodes, they just significant increase?
Yeah, so so the 4 meters of error is kind of the minimum that we're going for, the minimum amount of error, because anything less than that kind of falls within the error range given by GPS. Like if you just pulled your phone out and looked at the GPS, it's probably going to be somewhere in that range. So more nodes makes it get down closer to that 4 meters or less if we're lucky, but yeah. Yeah.
Do you know what that limit is? Right, you're saying 4 is a lot better than 3, but how much better is 5 than 4? Right, at some point, it's not gonna make a difference.
It depends on the number and exact arrangement of the nodes. For the scale of our test, we did see a couple meters of improvement. Most of those 8 and 9 meter large amounts of error we had were performed with 3 node setups. And when we increase the number of nodes, usually decrease. That does depend exactly on the orientation though. So it's difficult to give you a precise measurement for a general case.
At some point, it's gonna fall off pretty.
Yeah, so it does fall off eventually. We did not necessarily hit that point because when you scale up, and again, different arrangements might require more nodes.
Okay. Yeah, I think we're going to get okay, I will just say
Thank you.
Hello everyone, we are Capstone, and our project is including autonomous systems, sorting objects that you. Okay, so my name is Kevin. I was on the machinery side of the project.
My name is Tyler. I worked on embedded systems.
My name is Pat. I was systems.
I'm Vincent, and I worked on the control systems.
So there are 2 main strategies for waste collection. The first is single stream recycling. So this is the most convenient from an end user perspective because everything is thrown into the same bin. But this poses significant challenges for actually processing the waste and introduces the issue of contamination. The second strategy is multi-stream recycling, where every type of recyclable has its own receptacle. Even though this is great from a processing perspective, it's really challenging for people to know where to put their trash. And so because of this and other issues, less than a third of recyclable waste is actually ultimately recycled. So our goal with this project is to build a system with the processing efficiency of multi-stream recycling and the ease of use and convenience of single-stream recycling.
So our solution to this problem was to create a system that can sort trash autonomously and inexpensively on site. In this way, we can prevent contamination between different recyclable and non-recyclable streams, and we can also train for specific waste types at different sites. So for instance, in an office, you might have prevalence of paper and cardboard waste, so you can train your model to be specifically excelling at those waste types. Then that sorted waste can be sent to specialized facilities where they are actually adept at recycling that waste type instead of letting it end up in a landfill one day. The requirements of such a system would be to recognize and differentiate between different recycling items and physically separate them by sorting them into bins. And we also want this system to operate at the edge of self-sufficiency with limited space, power consumption, cost, and communication, because we want the system to be able to be deployed in multiple different environments and also to require low maintenance and low supervision.
So a brief overview. scrap sort comprises three main subsystems. The first is a computer vision system, which includes an onboard camera and a machine learning model that runs on a hardware accelerator for CNNs. The second is a set of ultrasonic sensors and a queuing system to keep track of items as they travel along the conveyor belt. And the third is a set of lever arms and motor controllers that physically push the items into their respective bins. So here's a quick video showing that happening. Okay, so let's dive a little deeper. This is a quick overview of how the system works in practice. So essentially, when the item is placed on the conveyor belt, it's seen by the ultrasonic sensor, which triggers the camera to start the machine learning model, begin running inference, and the predicted category is given to the queuing system. As the item travels along the conveyor belt, a set of ultrasonic sensors help keep track of where the item is. And when it arrives at its expected destination, the queuing system triggers the motor drivers to knock the item into its bin.
All right, so let's get into a little bit of hardware. Here we have our block diagram, and at the center of the block, we have our max 78,000 federal, and we have our onboard CNN accelerator, and as well as the and as you can see, we've integrated key protocols such as SPI for our LCD, GPIO for the ultrasonic sensors, I2C for the stepper motors, which specifically communicate with the chip controller, and as well as our power source, which powers both the conveyor belt, the microcontroller, and as well as the stepper motors.
Yeah, so at the center of the system, we have the MAX 78,000 feather development board. As you can see it here. This board comes with an onboard camera module, and then this is the microcontroller itself, which is called the MAX 78,000. And so the motivation for using this board is it's low power, low cost, small form factor, so that makes it suitable for edge applications. And then most importantly, the microcontroller itself has an integrated CNN accelerator, and this basically just makes it useful to do real-time computer vision on the microcontroller with another high speed, pretty hard. And then the accelerator also comes with toolkits, like software tools, so you can actually develop models to the constraints of the hardware. And then these are just some specs about the microcontroller itself, pretty comparable to other microcontrollers. Cortex 4, 512 kilobytes flash, 28 kilobytes SRAM, and 200 megahertz core clock speed.
So as I stated earlier, the ultrasonic sensors are what we use to keep track of our objects as they're moving down the conveyor belt by letting us know when they reach key locations. They have a simple and flexible interface that trigger interrupts when an object passes them, and then that can initiate a camera capture if the object is just placed on the conveyor belt at the beginning, so that it's outside, or if it's further down the conveyor belt, it can activate the stepper motor to actually lock the object off into its associated bin.
So initially, we actually thought about a pneumatic solenoid and actuator system, but unfortunately with that system, you need a bunch of different hardware like compressors or safety valves or regulators. And we wanted to do a live demo or, deploy this in an enclosed environment, and compressors get very loud. So we actually went with stepper motors instead, which are a special type of DC motor where you can actually control precisely in an open loop fashion the rotational position of the motor. And then another advantage of stepper motors is that you can actually change like the torque and the speed profiles by just controlling how fast you step it. And one con about this orientation, however, is unless you have a complicated, mechanical design, it's actually rotational, rotational movement instead of linear movement. So there can be a limited number of bidding arms on, a specific constrained environment.
And next we have our conveyor belt. We chose this conveyor belt specifically because it allowed us to have 3 different categories of classifications. As you can see, the bins attached to the side. And it also has an adjustable speed. Our max speed is about 30 meters per minute. So it goes decently fast. And we also have 80/20 attached to the side of the conveyor belt to allow us to attach the bins, stepper motors,
ultrasonic sensors, and then above the conveyor belt, we have our flashlight and the board, which is aimed down to capture images of items that are coming onto the conveyor belt.
So in order to power everything from a single outlet, American outlets, supply 120 volt AC. So we need to, downshift that to, DC in some way. So first we get that 120 volt AC from our conveyor belt, and we feed it to a power supply unit that down regulates it to 30 volt DC. This allows our stepper motors to get lots of power, and they're very torquey because of this. And then this 30 volt DC actually goes to a 5 volt buck converter that powers our ultrasonic, our microcontroller, and our flashlight for lighting.
Okay, so now I'm going to talk about some details of machine learning, which is how we actually identify objects. So first I want to talk about some of the constraints that capabilities of the accelerator to kind of distinguish object identification task a little better. So in general, the accelerators and launch chip are around peripheral, so they don't need to use an external protocol to communicate with it. And also in order to be efficient, accelerator uses low precision integer format, so we use int8 specifically. But because of that, we need to use quantitative error training, which is helpful because machine learning models are trained with point. So to get to 8-bit immediate quantized model, and we're losing information. So to retain the model's accuracy, we use special quantization error training. And then also, in general, the accelerator is limited to basic operations like 3x3 convolution kernels, row activation, and batch normalization. But this is plenty for building a classification model. And this is just showing some of the specs. So there's 432 kilobytes of memory for storing the weights of our model. So this basically forces us to develop our own architecture because even if you don't press the state-of-the-art model, it's not going to fit that. We have 512 kilobytes of data memory, so that kind of limits the dimensionality of the data as it propagates through the network. And also 50 megahertz clock speed. And then related to the data memory limitation, this basically limits us to 91 by 90 input image resolution. However, if you use a technique called streaming, which basically means you don't need to finish processing the input one before you start processing the next layer, you can actually increase the dimensionality. So we have a 128 by 128 input image, which is RGB, so 3 channels. So now I'm going to talk about the model development process. So one of the big challenges of working with live data is that it's highly variable. So like lighting, distortion, different objects. So you can't just expect that you'll train your model once and then just work robustly in real life. Because even if you get really good accuracy and you test it, that's not reflective of live inference, live data. So the first step in this process is to collect an initial data set. So we collected about 500 images per class. And this is not enough to get a robust model, but it's a good starting point. So what's important to note is that we wanted to collect data in the exact same environment that we're going to do inference in, because you want to train on data that is the same as what you're going to do inference on. So you're using them here. So yeah, once we collect an initial data set, this next step is optional, but I will also mention it. So it's called contrastive pre-training. And the idea here is that you want images that have the same sort of semantic meaning to have a good, close representation. So for example, if I take an image of a can and I augment it by distorting the color and blurring it, it's still a can, right? It's not a different class. So the idea of contrastive pre-training is you want images with the same semantic meaning to be close together. And what's also great about this method is you can do it in a self-supervised manner, so you actually don't even need any labels. So if you were to deploy this in real life, we can just collect a bunch of data as people are throwing away their trash. And we can use this contrastive pre-training method to get a very good representation of different classes without even needing labels. So then once we do contrastive pre-training, we actually want to do the task, which is classification. So here we actually do need labels, so you know what each object is. So we do fine-tuning for classification, and we basically train multiple models, different hyperparameters, and so on. And then we actually get the model to run on the board. So you have to do quantization and synthesis. And then the final step is evaluation and hard negative mining. So this is one of the most important steps because, like I mentioned earlier, just because we get good test accuracy and training, it's not mean that it's actually going to work on the board very well. It's just a lot of variation in real life. So what we do is something called hard negative mining. And basically that just means if I feed an image, so let's say I tell the board, we're going to feed you images of cans. And then it predicts, so it knows it's supposed to be a can, but if it predicts an image of, say, plastic, then we know, okay, that was a misclassified example. So we should add it to our data set because that's a hard example that the model is struggling with. So basically, repeat this process iteratively, and then we keep adding items to our data set that it misclassifies. And that's how we can get a pretty robust model. So this is our CNN architecture. It's a pretty standard traditional classification architecture. I don't know if you're familiar with VGT16, but it's sort of follows the same structure. Without getting too deep into the details, we have 10 convolution layers, 2 fully connected layers, for a total of about 278 kilobytes. That's our weight memory. That takes about 63% of the memory, so we could expand if we needed to. And then the total inference time is 13.5 milliseconds, so it's suitable for real-time classification. Okay, so now I'm going to talk a little about classification detection results and kind of how we overcame the challenges. So in general, the model will work pretty well if you have stable lighting, to classification and detection. But one of the problems is, we don't really have stable lighting. So for example, when we first started the project, a lot of the images feel very washed out. And also because the items are moving on a conveyor belt, that introduces some distortion. So we actually went into the camera settings and disabled the automatic exposure control and also decreased the exposure time. So that we have less distortion, but that comes at the cost of underexposed images, so we actually get out a flashlight to the images we properly expose. This kind of have to play around with it, but yeah. And then some details about our data set. We have about 4,000 images for classification, so about 1,000 per class. And then we also experimented a little bit with detection, so actually localizing objects to the bounding box. So we labeled about 500 images per class, but that's a very time-consuming process, so we only did it for a subset of the data set. I'm just going to show a demo of it doing classification. So you can see the conveyor belt's actually moving pretty fast, and it's not that much distortion. We get most of the items there. And then this is detection. So the main difference here is we actually put a bounding box around objects in addition to classification.
All right, and now we take a look at our system in action. We're going to see all those pieces come together and see how it turned out. Presenting reliability, I have moved to downtown, like, revenue, so they were very stable. Thank you for listening. We want to give some lots of acknowledgements and thank yous to our sponsor, the financial advisors, presenting to Rush, and everyone at the UCSB, our professors, PAs, and guests, and our sites. So yeah, thank you for listening. Any questions?
Since the default system expects some degree of volume from the pipeline through with the plastic and metal is to be expected, paper, some people are going to be trying to, some people won't. So that seems like maybe one area where, like, one material that will have like weakness in detection, or there are some characteristics that may not be obvious that where you need to improve classification.
Yes, so in anything, because the side of work is very well personal, and the like the lever arms and how what the size of the object doesn't matter. They also need to be like small enough so that our ultrasound detectors that will also like come back and give us some hey, there's something here. So yes, the size of the object is considered the size of the controller and people will have it. So that is something that we have to keep in mind. Yeah, does that make sense?
Yeah.
So I have a couple of questions. One was, the boundary boxing, do you
No, so the detection class is actually simpler than it looks because we only have one object in the frame and it's a black background. So really all I did is just add 4 extra outputs to the classification detection. And I just pre-trained the classification and defined for detection. So
classes that are not having a number I've seen the use of a word starting
I mean, it's dependent on whatever architecture you use.
but it doesn't.
Oh, yeah. So I mean, it has 432 kilobytes to your weight. So however, if you can make it like, for example, like you can do administrator has 6 classes.
Final layer.
Yeah.
Like 5 if you expand to 1 by 10.
Oh, I see what you're saying. So there, okay, I see. Yeah, so when you actually go from the convolution to the fully connected layer, you have to be flattening. So it is limited to 1,024 parameters. That's so I guess technically you could do 1,000. No, it's just five classes. Yeah. No, it can be more because you can flatten the CNN into a fully connected, but the limit of the hardware is that you can't have more than 1,024 parameters. Well, I don't know. I haven't tried.
Yeah, last question, do you find any difference so I'm wondering if the arrangement of the bin was kind of a random choice, or was that something where you said, oh, this is going to take a little bit longer?
So it was arbitrary, but in terms of the inference time, it's very consistent. So the inference time will be exactly the same, even if you just had a blank image. That's just how the structures are held. They're very consistent.
Yes, I will try with the folder,
Yeah, so our model is only good as our data set, and so we only really collected 4,000 images, and we could have collected more. It's kind of hard to know what the model's looking for. There are techniques you can use to say, like, oh, like, is there actually like a feature that activates with this class?